So it means how it looks and so how it looks. Quality in terms of customer expectation, but we also maybe patent considerations. Patent consideration to safeguard your invention. Okay, so these are the 5 non-monetary factors. There could be more. Okay, this is for questions number 1. Let's go to questions number 2. Okay, questions number 2. David needs 15 gallons of gasoline to top off his automobile's gas tank. If he drives an extra 8 mile round trip to gas stations on the outskirts of town, David can save 10 cents per gallon on the price of gasoline. Suppose gasoline costs $3.90 per gallon and David's car gets 25 miles per gallon for inter driving. Should David make the trip to get less expensive gasoline? Each mile that David drives creates 1 pound of carbon dioxide. Each pound of carbon dioxide has a cost impact of 2 cents on the environment. What other factors, costs, and otherwise should David consider in his decision making? Okay, so in these questions, David is dealing with 2 alternatives. So what other alternatives one or two of you give me the 2 different alternatives David is considering.
Drives an extra 8 miles and buy the cheaper gasoline.
Okay, so some of you say is it either make the trip or not, or whether to drive the extra 8 miles to get the gasoline at cheaper rate on the outskirts of town. Miranda, you said to get more expensive gasoline in town or cheaper one outside. Yes. Okay, these are the 2 alternatives: to buy in town or to buy out of town. So let's write it down. 2 alternatives. One is to obtain gas in town or obtain gas outskirts of town. Okay, let's consider these 2 alternatives and do the analysis. So we have alternative A, which is to purchase in town. What is the total cost of buying gas in town? So the total cost of buying gas in town be equals to what is the rate of gasoline in town? $3.90. $3.90 per gallon. Okay, and then how many gallons to top off the gas tank, to fill up the gas tank? 15. Yeah, it's 15 gallons. So the total cost of buying gas in town would be $58. Yes, good. So $58.5. Okay, $58.5. So and then now we look at alternative, which is to purchase the gas on the outskirts of the town. Yeah, to get the gas at lower rate, David must drive extra 8 miles. Okay, so drive extra 8 miles. Okay, so David must drive extra 8 miles. Okay, so that means he needs extra gas to drive that extra miles, right? So need extra gas for the extra 8 miles. So it is given that the mileage of the car is 25 miles per gallon. Okay, following is I'm going to show the formula to calculate the additional gas required to drive the extra 8 miles. You can see that 25 miles per gallon. Okay, so this means that 25 miles per gallon means 25 miles to travel the 25 miles. So 1 mile is equals to 1/25 gallons. Okay, and then 8 miles, how many gallons do you need? So 1/25 times 8 miles. So you get in total 0.32 gallons. Okay, for the extra 8 miles. You need 0.32 gallons of gas to travel the extra 8 miles. Okay, so therefore, David requires extra 0.32 gallons to get the gas at $3.80. It is 10 cents cheaper outcome. Okay, after determining the amount of gas required to travel that extra 8 miles, we can calculate the cost of buying gas on outskirts of the town. And we can calculate the cost of buying gas on outskirts of the town. And so the cost of gas is equals to $3.80 per gallon times. Okay, so this is the amount of gas to top off his gas tank. So 15 gallons plus the extra 0.32 gallons for the 8 miles. So you get a total of $58.216. Okay, apart from this, this is not the total cost of buying gas on outskirts of town because the cost of environment is not added yet. Okay, so the cost of environment is 0.0 is 2 cents per mile. So David drives 8 miles to get the gas at cheaper rate. Okay, so the total cost to the environment, the extra mile, 8 miles here, what is the cost to environment for the extra 8 miles? So it's $0.02 times 8 miles. You get 16 cents. Okay, so adding this cost with the cost of gas or buying gas on the outskirts here, you get what is the total? Get the total cost of obtaining gas at cheaper rate. Would be 58.216 plus 0.16 give you a total of 58.376. And what is your conclusions from this analysis? So the total cost of obtaining gas uptown would be $58 and $58.376 in comparison to $58.5 to get in town. So which one is cheaper?
Okay.
And what is your conclusion? So out of the town, right? Get the gas from outside the town will be cheaper. So your conclusions would be, okay, David, to get the less expensive gasoline. Okay, because the total cost of obtaining gasoline on the outskirts of town, which is 58.376, is less than the total cost of obtaining the gasoline in town, which is 58.50. Okay. Is that clear, the calculations? We can see that the difference is actually quite small, only a few, around, how many? Not more than 20 cents, right? And what other factors should David consider? Okay, what other factors should David consider to make the decision? So the question asks you, what other factors should David consider in his decision making? So the factors that David should consider also at the same time would be, for example, cost of maintenance, cost of, sorry, my writing isn't very nice, really not used to write on tablet. Okay, so cost of, if you can't read my words, you can ask again. The risk of accidents, good, and also, for example, traffic jam. When there is traffic jam, the cost of gasoline, the consumptions of gasoline will increase. Okay, other example would be opportunity, cost of time. That means you can he probably can spend the time for other things that he like to do, okay, rather than to just spend the time to travel out of town to get the gas, okay, and also maybe depreciation of car, okay, the more he drives, the higher is the mileage, and next time the resale value will be reduced if the mileage is higher. And yeah, and then I think that's about it. Cost of maintenance, insurance, risk of accident. He might have one accident, and this might add to the extra cost. The traffic jam, opportunity cost of time, and depreciation of car. And then these are all the factors that he may want to consider before making the final decision. Okay, so we are done with questions number 2. Now let's have a look at questions number 3. The decision was made by NASA to abandon rocket launch payloads into orbit around the Earth. We must now rely on Russians for this capability. Use the principle of engineering economy to examine the decisions. Okay, so in these questions, you are required to apply the 7 principle of engineering economy. And for this type of questions, you can just write something short. Apply each of these principle. Okay, for example, what is the principle of engineering economy? Number 1, principle 1. You remember?
Develop the alternative.
Okay. So the principle number 1 is develop the alternatives. Yes. Okay, develop the alternatives. Okay, so for this principle 1, it would maybe lead to numerous other means. Will lead to numerous other means for launching payloads into space. For example, okay, now that NASA cannot do it, maybe we can choose to use private US or foreign firms to carry out the task. Okay, so these are example of your alternatives. How about principle number 2? What is principle 2 of engineering economy analysis?
Focus on the differences.
Yes, focus on the differences. So when how do you focus on the differences? So here we normally will do cost analysis, cost and benefit analysis. Okay, for example, we can focus differences in cost and the benefit of alternative launching methods to be identified and measured. Okay. And the third principle,
Use a consistent viewpoint.
okay, use consistent viewpoint. With in this principle, we can establish a consistent viewpoint to be utilized in the analysis of launching methods. If, for example, from the perspective of U.S. government, if we have this consistent viewpoint from one perspective, then it's easier for us to have a consistent like cash outflow, inflow. Okay, and so it will be different. Let's say if you have a bank that is giving out loan. So sometimes this analysis can be done from the perspective of bank or from the perspective of the person who get the loan. Okay, and so in terms of the cash analysis, the cash outflow and inflow will be slightly different from these two different viewpoints. So we will have a look at this perhaps in the third week or fourth week of study. Okay. So now we take a look at principle 4. What is principle number 4? Principle 4 is about use of common unit of measure. Okay, normally when we consider the alternative, we will try to use one common unit of measure, and that common unit of measure is normally the monetary, okay, the amount of cost or the amount of benefit you get. You will reduce the cost and benefit identified by principle 2 to common unit of comparison, normally in dollars or other monetary units. After this, we have principle 5. Okay, principle 5 is about consider all the relevant criteria. We ensure that no significant criteria in evaluating alternatives are overlooked. And then, principle 6 is about make uncertainty explicit. Here we can identify risk associated with each alternative, including them in the analysis of critical importance. And finally, principle 7, we need to have a close look. We'll revisit the decision. Okay, the decisions this principle 7 here allows the analyst to determine how good or poor a decision made and why. Okay, this could impact on subsequent decision making. And normally we have this group in a close look. Whenever you make a decision, this decision will be something like we refer in the future to improve our next analysis. Okay. So okay, we are done with questions number 3. Now, can we move on questions 4? Okay, let's take a look at these questions together. Here, a typical discounted price of AAA battery is 75 cents. It is designed to provide 1.5 volts and 1 amperes for about an hour. Now we multiply volts and amps to obtain power of 1.5 watts from the battery. Okay, thus it costs 75 cents for 1.5 watts hours of energy. How much would it cost to deliver 1 kilowatt hour? How does this compare with the cost of energy from your local electric utility of 10 cents per kilowatt hour? Did someone talk about this question is confusing? Okay, may I know how many of you managed to get the answer? Okay, what is your answer? Can all of you show me your answer? You can type in the chat box on the right. Okay, can you type the answer? How much would it cost to deliver 1 kilowatt hour using the AAA battery? Yes, good. $500. This question isn't very difficult. Maybe you can we can go through it briefly. So cost per watt hour is equals to 0.75 cents per 1.5 watt hour. So this is equivalent to 50 cents per watt hour. Okay, so at the cost of 50 cents per watt hour, it will cost, we have 1000 watt hour, and it is 50 cents per watt hour. And so this gives you a total of $500 per kilowatt hour. For the power from this is power from a single AAA battery. So how does it compare to the cost of from the local electric utility at 10 cents per kilowatt hour? Okay, so it's, let's say, 10 cents per kilowatt hour. So here we have from the battery is $500 per kilowatt hour. But for the local utility, it is 10 cent per kilowatt hour. Okay, which means that this is power from the single AAA battery is a lot more expensive than the power from the local utility. Huh? So this is about how many times? And this is about 5,000 times more costly than energy from local utility. Okay, so comparing the two, this is 5,000 times more costly. Okay, yeah, there is answer for questions 4. Is that clear to you? So let's proceed to questions number 5, the last questions of the tutorial. Okay, so Henry Ford's Model T was originally designed and built to run on ethanol. Okay, today ethanol can be produced with domestic stills for about 85 cents per gallon. When blended with gasoline costing $4 per gallon, a 20% ethanol and 80% gasoline mixture costs $3.37 per gallon. They assume fuel consumptions at 25 miles per gallon and engine performance in general are not adversely affected with this 2080 blend, which we call E20 fuel. How much? Question A asks, how much money can be saved for 15,000 miles of driving per year? And how much gasoline per year is being saved if 1 million people use the E20 fuel? Okay, let's take a look at questions A. So you are given a lot of information here. Let's summarize the informations. Okay, we have cost of gasoline. The cost of gasoline is how much? What is the cost of gasoline?
$4.
Then $4 per gallon. How about the cost of ethanol?
85 cents.
Yeah, 85 cents per gallon. Okay, and then the cost of E20, the blend. Okay, with the mixture of ethanol with the gasoline, it reduces the price of this blend to $3.37 per gallon. Okay, and then the fuel consumption. Fuel consumption is equals to 25 miles per gallon. And then the distance traveled per year. The distance traveled is the 15,000 miles per year. And so we can first compute. The question asks you how much money can be saved for 15,000 miles of driving per year. And here you need to convert the fuel consumptions. 25 miles per gallon. Also, you need to convert this 15,000 miles per year, the distance here, into the total amount of fuel consumptions in gallon per year. Okay, so we'll first compute fuel consumption per year in gallon. And this is equals to 15,000 miles per year divided by the knowledge 25 miles per gallon. You get 600 gallons per year. Okay, and then we can then compute the total saving. Okay, the total savings would be the fuel consumption per year, and multiply with the saving per gallon. Okay, so you have found the fuel consumption is equals to 600 gallons per year. You can just bring the values in here. We have 600 gallons per year multiplied with fuel savings per gallon. What is the total amount of savings per gallon? It would be how much?
60%?
So it's $4 here minus $3.37. You can have 4 minus $3.37. And then what is the total of savings? It will be $378 per is the total amount of savings. Okay, is it clear so far? Okay, if no questions, then we proceed to B. What is the B about? How much gasoline per year is being saved if 1 million people use E20 fuel? So you can see that 20% of gasoline is substituted with ethanol per gallon in E20. Okay? Therefore, out of the 600 gallons fuel consumed per year, then we can save how much gasoline? 0.2. Okay, this 0.2 here stands for 20%. Out of 600 gallons per year, we can save 120 gallons per year of gasoline. Okay, so this is per percent. So if there's 1 million people use E20 fuel, how much is the saving in total? Okay, if 1 million people use E20 fuel, the gasoline saved would be 120 gallons per year. Okay, so this is from up here times 1 million. So you can save 120 million gallons per year. Okay, so this is the final answer. Any questions? So far so good? Oh good, huh? Okay, good. So, and do you actually need this recording, or are you good so far? You don't need me to send you the stations, the recorded stations for this class? You need the recorded stations? Okay, so I will send the recorded stations later. Maybe share in the link. If you want to take a look, you take a look. Okay, so for those who miss out these stations. And yeah, that's about the tutorial number 1. And perhaps I will quickly browse through the lecture number 2 with you. So I have pre-recorded lecture number 2 and put in Spectrum. Give me a moment to pull it out. Okay, so you have for lecture 2, okay, for lecture this week it will be about cost concept. You learn about different type of cost and also some design. Let's see. We'll go through briefly. Then here I have also included tutorial 2 for you to try. Then we will discuss tutorial 2 next week. If you have any questions, you can post your question here. Okay, this is locations where you can submit your tutorial 2. Huh? And remember the submissions for tutorial 1 will be this, the deadline will be this afternoon 5 o'clock. Okay, please don't forget to submit. Okay, let's see the lecture number 2.
By the way, Doctor,
Yes?
in the spectrum for tutorial 2, it shows the deadline today as well.
Deadline today is 20 tutorial 2. Wait.
Yeah, when you open it, it shows today the deadline.
Today is the deadline. You mean the submission link?
Yes.
I will set it at the moment. 23rd, 5 o'clock 23rd. Okay, thanks for informing. I didn't realize about this. Okay, alright, it should be now 23rd of March till that. Tutorial 2. Okay, so the due date has been set to 23rd of March. Okay, so for today's lecture is about cost concept and design economics. So initially you learn about the different type of cost Okay, you need to familiar yourself with what are the direct material, direct level, overhead costs, incremental costs. Okay, and then you learn about, there are some examples given to you lah, to understand further. And I try to illustrate this in detail. You can take a look later. And recurring and non-recurring cost. And I think the most important it would be this. Okay, the equations used to calculate price demand. Okay, price as a function of demand. And then total revenue functions. And then cost volume and break-even point relations. Okay, these are some of the common questions that you need to look into. And especially this graph, how do you determine the break-even point number 1 and break-even point number 2? Okay, and this is a total revenue. You have different costs, you have fixed costs, you have variable costs that are add up to the total cost. And then with this total revenue, again from this total revenue and the total cost, you can determine the break-even point 1 and break-even point 2. So the calculations will involve some calculus now. So I believe you have gone through calculus, right? Engineering mathematics 1 and 2 should have you gone through both engineering mathematics 1 and 2? Okay, good. So you should be able to do the calculations and understand in first derivative and second derivative. Okay, please go through the example. If you have any questions, you can ask me again next week. And so there are two scenarios that you will go through. And the first scenario is demand as a function of price. And then the second scenario is about price and demand are independent of each other. Okay, these two scenarios will use different equations to do the calculations. Okay, this is scenario 2. We don't have so we only have one break-even point. We only have one break-even point. And the total revenue is not a curve, it's not a quadratic shape. It is a straight line in this scenario 2. And after that, okay, cost-driven design optimizations. I think this is quite relevant to engineers. When you do the design, how the design parameters affect the cost. And you will need to go through this. I think tutorial 2 will have 1 or 2 questions required to you to do this cost-driven design optimization. And then finally is the present economy studies. Okay, how do you perform present economy studies? Present economy studies means you do the analysis over a short period of time, maybe within a year, where the time value of money is insignificant. Okay, and then normally you have 2 rules to be applied. Okay, so for each of these rules, I have given you one example. When do you apply the rules? Okay, that's all about it. So please go through the video recording. Alright, and then do the tutorial. We shall discuss next week. Okay, do you have any questions? Any more questions? If there's no more questions, then I will end this session. Hello? No more? Okay. Then I'll see you again next week. Okay, bye-bye.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Good morning, students. This week we are going to look at cost concept and design economics. At the end of this topic, you should be able to analyze short-term alternatives when the time value of money is not a factor. The time value of money is the concept that money available at present time is worth more than the identical sum in the future due to its potential earning capacity. This core principle of finance holds that, provided money can earn interest, any amount of money is worth more the sooner it is received. But this week, we'll look at the analysis of short-term alternatives, not considering time value of money just yet. We accomplish such analysis using two types of scenarios: the economic break-even analysis and the present economic studies. There are a variety of costs to be considered in an engineering economic analysis. These costs differ in their frequency of occurrence, relative magnitude, and degree of impact on the study. Today we'll look at a number of cost categories and illustrate how they should be treated in an engineering economic analysis. These include direct labor cost, factory overhead cost, and direct material cost, and so on. How do we calculate the cost to make nasi lemak? Do we just sum up cost of all ingredients? How about labor cost, cost of electricity, gas, and etc.? How do we categorize these costs? Now we will look at a few categories of cost and what the categories contain. What are fixed costs? Fixed costs are those that do not fluctuate with changes in production level or sales volume. Fixed costs are independent of output. Typical fixed costs include insurance and taxes on facilities, buildings, lands, equipment, payments on loans, license fees, general management and administrative salaries, and advertising. Of course, any cost is subject to change, but fixed costs tend to remain constant over a specific range of operating conditions. While larger changes in usage of resources occur, or when plant expansions or shutdown is involved, fixed costs can be affected. Variable costs are those that respond directly and proportionally to changes in production level or volume. Variable costs vary with output. For example, the cost of raw material and hourly production wages used in a product or service are variable costs because they vary in total with the number of output units, even though the cost per unit stay the same. Apart from this, sales commissions, inventory, packaging supplies, and shipping costs are all variable costs. An incremental cost is the additional cost that results from increasing the output of a system by one or more units. Incremental cost is often associated with go or no-go decisions that involve a limited change in the output or activity level. For instance, a factory's workforce is working to full capacity. Adding just one more unit to output would either require paying overtime or spending money on recruiting new staff. Also, there may be additional costs added to overhead such as water, electricity bills, and etc. In engineering economic analysis, we look at cost and also revenue. What do you understand about revenue? Revenue is the income generated from sales of goods or services or any other use of capital or assets associated with the main operations of an organization before any costs or expenses are deducted. Now let's take a look at one example on fixed and variable cost. In connections with surfacing a new highway, a contractor has a choice of two sites on which to set up the asphalt mixing plant equipment. The contractor estimates that it will cost $1.15 per cubic yard per mile to haul the asphalt paving material from the mixing plant to the job location. Factors relating the two mixing sites are as follows. Assuming the production costs at each site are the same. The cost factor includes average hauling distance. To site A is equals to 6 miles, to site B is equals to 4.3 miles. The monthly rental of site is $1,000 for site A and $5,000 for site B. The cost to set up or remove and remove equipment is equals to $15,000 for site A and $25,000 for site B. The hauling expenses is $1.15 per cubic yard per mile for both site A and site B. The flag persons is not required in site A but required in site B, which costs $96 per day. Okay, the job requires 50,000 cubic yards of mixed asphalt paving material. It is estimated that 4 months, equivalent to 17 weeks of 5 working days per week, will be required for the job. Compare the two sites in terms of their fixed, variable, and total cost. Assume that the cost of the return trip is negligible. Which is the better site? You need to find out. Okay, for the selected site, how many cubic yards of paving materials does the contractor have to deliver before starting to make a profit if paid $8.05 per cubic yard delivered to the job location? Let's illustrate this example. We have site A and site B with the cost factors listed. Distance from site A and site B to the job locations are 6 miles and 4.3 miles respectively, and the hauling cost is $1.15 per cubic yard per mile. The job locations requires 50,000 cubic yards of paving materials, and it is estimated that 4 months is required to complete the job, and these 4 months is equivalent to 17 weeks of 5 working days per week. The payment to contractor for the job is $8.05 per cubic yard. Out of all the cost, the site rent, setup and removal cost, and the cost of the flag person at site B would be constant for the total job, and these costs are considered fixed cost. On the other hand, the hauling cost is considered a variable cost, as it would vary in total amount with the distance and therefore the total output quantity. The total rent at site A here is obtained by multiplying 4 months of job with $1,000 of monthly rent. A similar calculations is applied for the total rent at site B to get $20,000. For the flag person at site B, the daily wages is $96 per day. This is translated to $8,160 for a period of 17 weeks, which contains 85 days. The hauling cost at site A is obtained by multiplying the hauling distance with the total volume of paving material required in cubic yard and the hauling cost per cubic yard per mile. The total cost is $345,000 for site A, and similar formula is applied for site B to get the hauling cost of $247,250. The total fixed cost for site A is equals to $19,000 by summing the rent and the setup and removal cost. Whereas for site B, the total fixed cost is much higher at $53,160 by summing not only the rent and the setup and removal cost, but also the cost for the flag person. The total cost for both sides can be calculated as the summations of fixed cost and variable cost. Now we can see that although site B has a larger fixed cost, it has a smaller total cost as compared to site A, because the extra fixed costs of site B are being traded off for the reduced variable cost at this site, simply because site B is located closer to the job location. And since site B incurs less cost in total than site A, therefore site B is considered a better choice. For the selected site, which is site B, we can calculate the unit variable cost of paving material delivered. This unit variable cost is $4.945 per cubic yard. Subsequently, we can compute the total volume of paving material the contractor have to deliver before starting to make a profit. The contractor will begin to make a profit at a point where total revenues equals total cost as a function of the volume of material delivered. X here is the volume of paving material delivered before the contractor starts to make a profit. This is the total fixed cost, and this is the unit variable cost. And this is the payment per cubic yard of material provided to the contractor. Therefore, by using site B, the contractor will begin to make a profit on the job after delivering 17,121 cubic yards of paving material. Cost can also be divided into several types, including recurring and non-recurring costs. Recurring costs are those that are repetitive and occur when an organization produces similar goods or services on a continuing basis. Variable costs are also recurring costs because they repeat with each unit of output. A fixed cost that is paid on a repeatable basis is also a recurring cost. Example of recurring cost is the office space rental. Non-recurring costs, on the other hand, are those that are not repetitive. For example, purchase costs for real estate upon which a plant will be built, cost of installing a new machine, emergency maintenance expenses, and etc. We can also categorize the cost to direct and indirect costs. Direct costs are those that can be reasonably measured and allocated to a specific output or work activity. The labor and material costs directly associated with a product, service, or construction activity are direct costs. For example, the materials needed to make a pair of scissors is considered a direct cost. Indirect costs, on the other hand, are costs that are difficult to allocate to a specific output or work activity. They are normally allocated through a selected formula, for example, as a proportion to direct labor hours, direct labor dollars, or direct material dollars. For example, cost of common tools, general supplies, equipment maintenance in a plant are all considered indirect costs. Overhead costs. Overhead costs may be allocated to total plants, departments within a plant, and a given item of equipment. These costs consist of plant operating costs that are indirect material and indirect labor costs, insurance premiums, rentals, utilities, general repairs, property taxes, depreciations, and supervision. Standard costs are representative costs per unit of output. They are established in advance of actual productions or service delivery. They are developed from the direct labor hours, materials, and support functions, with the established cost per unit planned for the production or delivery process. Standard costs play an important role in cost control and other management functions. Some typical uses include estimating future manufacturing costs, measuring operating performance by comparing actual cost per unit with the standard unit cost, preparing bids on products or services requested by customers, and last but not least, establishing the value of work in process and finished inventories. This is an example on the calculations of standard cost. The company expects to produce 13,200 gallons during the year at normal capacity. It takes 2 direct labor hours for each gallon. Here shows the budgeted overhead costs consisting of variable and fixed costs. The amount of variable and fixed costs are $79,200 and $52,800 respectively, and the total amount of budgeted overhead costs is $132,000. The standard direct labor hours is 26,400 hours. The calculations of overhead rate per direct labor hour is given by the amount divided by the total number of direct labor hours. And with these calculations, you get $3 of variable cost per direct labor hour and $2 of fixed cost per direct labor hours. To calculate the standard manufacturing overhead rate per gallon, you can just divide the total amount of budgeted overhead costs by 13,200 gallons to get $10 per gallon. Or you can just multiply this $5 here with 2 hours because it takes 2 direct labor hours for each gallon. Measures of economic worth. Goods and services are produced and desired because they have utility, which means the power to satisfy human wants and needs. And thus, they may be used or consumed directly, or they may be used to produce other goods or services. Much of our business activity, including engineering, focuses on increasing the utility of materials and products by changing their form or locations. For example, iron ore, worth only a few dollars per ton, can be significantly increased in value by being processed, combined with suitable alloying element, and converted into razor blades. Rice, when combined with sambal, ikan bilis, and peanuts, can be used to produce nasi lemak and sold at higher price. Similarly, snow worth almost nothing when found in high distant mountain becomes quite valuable, but it is delivered in powder form several hundred miles away to dry area. Engineering economic analysis is important as a tool to project the profits and loss that may be incurred in these activities. Most general economic principles are stated for situations in which perfect competitions exist. Perfect competitions occurs in situations in which any given product is supplied by a large number of vendors, and there is no restrictions on additional suppliers entering the market. Under such conditions, there is assurance of complete freedom on the part of both buyer and seller. Monopoly is opposite from perfect competition. A perfect monopoly exists when a unique product or service is only available from a single supplier, and that supplier can prevent the entry of all others into the market. Under such conditions, the buyer is at the complete mercy of the supplier in terms of the availability of the product and the price of the product. Perfect monopolies rarely occur in practice because few products are so unique that substitutes cannot be used satisfactorily, and the government regulations prohibit monopolies if they are unduly restrictive. Goods and services may be divided into two types: necessities and luxurious. Obviously, the terms are relative because for most goods and services, what one person considers a necessity may be considered a luxury by another. For example, a person living in one community may find that a car is a necessity to get to and from work. If the same person lives and works in a different city, adequate public transportations might be available and a car would be a luxury. For all goods and services, there is a relationship between the price that must be paid and the quantity that will be demanded or purchased. This is the relationship between price and demand, and it can be expressed as a linear function P equals to A minus BD. And D takes a value from 0 to A divided by B, and both A and B has value larger than 0. Okay, A is the intercept on the price axis and minus B is the slope. Okay, B is the amount by which demand increases for each unit decrease in the price. Okay, both A and B are constant. Hence, we can compute the demand using these equations: A minus P divided by B for B not equals to 0. As we can see, when the price drops, units of demand increases. The total revenue TR that will result from a business venture during a given period is the product of the selling price per unit P and the number of units sold D. And therefore, we can write the total revenue as a function of demand by replacing P here with equations 1 from previous line. And the demand D that produces the maximum total revenue can then be solved by these differential equations. Here we differentiate total revenue with respect to the demand and equates this to 0. Okay, by rearrangement, we get the demand D that produces maximum total revenue to be A divided by 2B. As can be seen, calculus can help to determine the demand that maximizes revenue. By differentiations, or in other words, compute the first derivative of total revenue with respect to the demand, we can solve for the optimal demand, which is A divided by 2B. Okay. And then this is the plot of total revenue versus demand. As can be seen, the optimal demand occurs at A divided by 2B, and the total revenue is maximized at A squared divided by 4B. It must be emphasized that most businesses would not obtain maximum profits just by maximizing revenue. Okay, the cost-volume relationship must be considered and related to revenue because cost reductions provides a key motivations for many engineering process improvement. Now let's take a look at cost, volume, and break-even point relationship. At any demand, the total cost is the summations of the fixed cost and the variable cost. The fixed costs remain constant over a wide range of activities, but variable costs vary in total with the volume of output. Variable cost is given by this linear relationship, which is the product of the variable cost per unit and the demand. Break-even points, or BEP, is the sale amount in either unit or revenue terms that is required to cover total cost, which include both fixed and variable cost. The main purpose of break-even analysis is to determine the minimum output that must be exceeded in order to make profit. We can also use this analysis as a rough indicator of the earnings impact of a marketing activity. Break-even analysis helps to provide a dynamic view of the relationship between revenue, cost, and profits. And now we consider two scenarios for finding break-even points. In the first scenario, the demand is a function of price. In the second scenario, the price and demand are independent of each other. Now let's consider the first scenario, the demand as a function of price. When the total revenue and total cost are combined, the typical results as a function of demand are shown here. Okay, the blue curve here is the total revenue, and the blue line here is the total cost. Okay, the horizontal line indicates the fixed cost, whereas the height between the total cost and the fixed cost refers to the variable cost. At break-even point D'1, the total revenue is equal to the total cost, and a further increase in demand will result in a profit for the operations, as shown by the shaded area here. Then at optimal demand, D*, the profit is maximized. At break-even point D'2, the total revenue is again equal to the total cost. However, additional volume will result in an operation loss instead of a profit. Obviously, the conditions between which the break-even points and maximum profit occurs are our primary interest. Now let's consider the first scenario, the demand as a function of price. When the total revenue and total cost are combined, the typical results as a function of demands are shown here. The blue curve here refers to the total revenue, and the blue line here refers to the total cost. The blue horizontal line here indicates the fixed cost, whereas the height between the total cost and the fixed cost refers to the variable cost. At break-even point D'1, the total revenue is equals to the total cost, and a further increase in demand will result in a profit for the operations, which is shown by the shaded area here. Then at the optimal demand, D*, profit is maximized. At break-even point D'2 here, the total revenue and total cost are again equal, but additional volume will result in an operation loss instead of a profit. Obviously, the conditions between the two break-even points and the maximum profit occurs are our primary interest. To compute the optimal demand at which the maximum profit occurs, we consider the following. At any volume or demand D, profit or loss is equals to total revenue minus total cost. By replacing the equations in previous slide into these equations, you get this for D in between 0 and A divided by B. In order for profit to occur, based on these equations, and to achieve the typical results depicted in the previous figure, two conditions must be met. A minus CB must be larger than 0, which means that the price per unit that will result in no demand, which is A, has to be greater than the variable cost per unit, which is C subscript V. The total revenue must exceed total cost for the period involved. If these conditions are met, we can find the optimal demand at which the maximum profit occurs. We find the optimal demand by differentiating profit with respect to the demand and set this to 0. We get the optimal demand D*3 equals to A minus CV divided by 2B. A here is the intercept and B is the slope in the price demand function, and CV here is the variable cost. To ensure maximized profit, the sign of the second derivative must be negative, which means this will be negative for B with a value larger than 0. As seen in the graph, the break-even points for an operations occur when total revenue equals total cost. Therefore, to find the break-even points, we equate total revenue to total cost and end up with a quadratic equations with unknown D. We can solve for the break-even points D'1 and D'2 as the roots of the equations by using this formula. With the static conditions for a profit satisfied, the quantity in this bracket will be greater than 0. This will ensure that D'1 and D'2 have real positive and unequal values. Let's do one simple exercise. A company produces an electronic timing switch that is used in consumer and commercial products, but by several other manufacturing firms. The fixed cost is $73,000 per month, and the variable cost is $83 per unit. The selling price per unit is given by this formula, based on the previous equation, which is P equals to A minus BD. Okay, for these situations, determine the optimal volume for this product and confirm that a profit occurs instead of loss at this demand. And then find the volume at which break-even occurs and the range of profitable demand. To determine the optimal volume for this product and confirm that a profit occurs instead of loss at this demand, we can do the following. We can first extract out the information from the equations. Here we have the fixed cost equals to $73,000, the variable cost equals to $83 per unit, and this is the price as a function of demand equations. And from these equations, we can extract out A equals to $180 and B is equals to 0.02. Okay, to determine the optimal volume to result in a profit, we can make use of this formula. Okay, by substituting the values in this formula, we get the optimal volume equals to 2,425 units per month. Okay, remember there are two conditions to meet in order to get a profit. Okay, the first conditions to meet is A minus the variable cost larger than 0. Okay, from this formula, we get a value of $97, which is greater than 0. And the second condition is total revenue minus total cost is greater than 0 for this demand. And we can make use of these equations, the profit equation. The profit equals to total revenue minus total cost. And this part of the equations is the total revenue, and this is the total cost. Okay, since the total revenue is greater than the total cost, we get a profit of $44,612. And we can conclude that a demand of 2,425 units per month result in a maximum profit of $44,612 per month. Okay, we can also use another way, the second derivative, to confirm whether this value is a profit or a loss. So we can differentiate this equation twice to get the second derivative, which is equals to minus 2b. Okay, b is 0.02. So at the end, substituting b into the equations, the second derivative equations, we get a value of minus 0 or negative 0.04. And since the value of the second derivative is negative, okay, we confirm that this value here is indeed a profit rather than a loss. The second task is to find the volumes at which break-even occurs and the range of profitable demand. Okay, we know that the break-even points occur when the total revenue is equals to total cost. Okay, therefore, to find the break-even points, we equate total revenue to total cost and end up with these quadratic equations with unknown d. Okay, to find out d, which is the break-even points, we can make use of this formula to calculate the roots. Okay, the roots of these quadratic equations are the break-even points that we are looking for. Okay, so this will result in the first break-even points occur at 932 units per month, and the second break-even points occur at 3,918 units per month. Okay, therefore, the range of profitable demand is from 932 units per month to 3,918 units per month. Now let's take a look at scenario 2, whereby the price and demand are independent of each other. Okay, when the price per unit P for a product or service is independent of demand and greater than the variable cost per unit, a single break-even point results. Okay, then under the assumptions that demand is immediately met, total revenue is equal to the product of price per unit and the demand. If the linear relationship for cost in equations 7 and equations 8 is also used in the model, the typical situations is depicted in the next slide. This is a typical break-even chart when the price is a constant. Shown here is the total revenue, total cost, and the fixed cost. And the height in between the total cost and fixed cost corresponds to the variable cost. The break-even point is the point at which the total revenue is equal to the total cost. And if we have a demand or volume greater than the break-even point, we make a profit. Otherwise, we make a loss. Okay, to compute the break-even point, we can equate total revenue to total cost and find out the demand. Okay, so the total revenue here is just the product of price per unit and the demand. And the total cost consists of the fixed cost and the variable cost. The break-even point is equals to the fixed cost divided by price per unit minus variable cost. This is an exercise for scenario 2. An engineering consulting firm measures its output in standard service hours unit, which is a function of the personnel grade level in the professional staff. The variable cost is $62 per standard service hour, and the charge-out rate or the selling price is $55.56 per hour. The maximum output of the firm is 160,000 hours per year, and its fixed cost is $2,024,000 per year. You are given two tasks here. For task A, for this firm, what is the break-even point in standard service hours and in percentage of total capacity? For task B, you are required to calculate the percentage reductions in the break-even point if fixed costs are reduced 10% and if variable cost per hour is reduced 10%. Okay, this is the solutions for task A. Okay, for this firm, what is the break-even point in standard service hour and in percentage of total capacity? Okay, here are the informations we gather from the equations. Here you can see that the price per unit is equal to $85.56 per hour and is independent of the volume or the OD. That's why we consider these questions as a scenario 2. Okay, so this is the variable cost, which is $62 per standard service hour. D is the total output, which is 16,000 hours per year, and this is the fixed cost, which is about $2 million per year. Okay, to find the break-even point, we equate the total revenue to total cost, and this total revenue is just given by the product of price per unit and the demand. And then from these equations, we can calculate the break-even point in standard service hour, which is equal to 85,908 hours per year. And this is the break-even point in percentage of total capacity. So the total capacity is 160,000 hours per year. So these are 85,908 hours here. It's actually fulfilling only 53.7% of the total capacity. Now we'll take a look at cost-driven design optimization. Very often, engineers are involved in the design of products, services, and processes. They must consider the cost in these designs. Cost minimization through effective design are plentiful in practice of engineering. For example, the design of a heat exchanger in terms of tube material and tube configuration could significantly affect the dissipations of heat and therefore the cost. Cost-driven design optimizations is critical in today's competitive business environment. We'll look at the procedure for determining an optimal design using cost concept. In brief, we'll look at a discrete and continuous optimization problem that involves a single design variable, which is also known as the primary cost driver. The two main tasks involved in cost-driven design optimizations are as follows. First, determine the optimal value for a certain alternative design variable. For example, what velocity of an aircraft minimizes the total annual cost of owning and operating the aircraft. The design variable here would be the velocity of an aircraft. The second task is to select the best alternative, each with its own unique value for the design variable. For example, what insulation thickness is best for a home in Virginia? R11, R19, R30, or R38. These four are the four different alternatives. And the design variable here would be the insulation thickness. For design optimizations, we can develop a cost model or write the expressions of the cost model in terms of the design variable X. X here is the primary cost driver. If we have the knowledge of the behavior of the primary cost driver, we'll be able to use it to account for a large portions of the total cost behavior. Optimizing a design with respect to cost is a 5-step process. Step 1 involves identifying the design variables that is the primary cost driver. Any design parameters for a product could be identified as the primary cost driver if they affect the cost the most. An example of a design variable could be pipe diameter, insulation thickness, and so on. Step 2 involves expressing the cost model in terms of the design variable. And step 3 involves setting the first derivative of the cost model with respect to the continuous design variable equals to 0. In other words, we differentiate the cost model with respect to the continuous design variable. For discrete design variables, on the other hand, we can compute the value of the cost model for each discrete value over a pre-selected range of potential values. Step 4 involves solving the equations found in step 3 for the optimum value of the continuous design variable. For discrete design variables, the optimum value has the minimum cost value found in step 3. For step 5, for continuous design variables, we can use the second derivative of the cost model with respect to the design variable to determine whether the optimum value found in step 4 minimizes or maximizes the cost. If the second derivative has a negative value, the optimum design variable found is set to maximize the cost. On the other hand, if the second derivative has a positive value, the optimum design variable found is set to minimize the cost, which is desirable. Here is a simplified cost model with single design variable X. In general, the cost models consist of 3 types of cost. Fixed cost, cost that vary directly with the design variable, and the cost that vary indirectly with the design variable. And K here represent the fixed cost. A here represent the cost that vary directly with the design variable, and B here represent the cost that vary indirectly with the design variable. Let's take a look at one example on cost-driven design optimization. How fast should the airplane fly? The cost of operating a jet-powered commercial passenger-carrying airplane varies as the 3/2 power of its velocity. Specifically, CO is equal to KNV to the power of 3/2, where N is the trip length in miles, K is the constant of proportionality, and the V is the velocity in miles per hour. It is known that at 400 miles per hour, The average cost of operations is $300 per mile. The company that owns the aircraft wants to minimize the cost of operation, but that cost must be balanced against the cost of the passenger's time, which is CC, which has been set at $300,000 per hour. Okay, there are two questions for you. Question A. At what velocity should the trip be planned to minimize the total cost, which is the sum of the cost of operating the airplane and the cost of passengers' time? Task B. How do you know that your answer for the problem in part A minimizes the total cost? Here shows the solutions for question A. The equations for the total cost is given by the summations of the cost of operating the airplane and the cost of the passenger's time. The cost of operating the airplane is given by this formula, and the cost of the passenger's time is given by the product of the rate per hour and the time spent on the trip, which is given by N divided by B. The unit for N divided by B is in hours. The design variable for this problem is velocity V. Before we can find the optimal value for the design variable V that minimizes the cost, we'll first need to solve for K, which is the constant of proportionality. This is the formula for the cost of operating the airplane. By rearranging the formula, we get CO divided by N, and this is actually the average cost of operating the airplane. Remember, in the equations we are given these informations. At 400 miles per hour in the velocity, the average cost of operations is $300 per mile. By substituting these informations into this formula and work all the way down, we'll end up with K equals to 0.0375 in units of dollars, hours to the power of 3 halves per miles to the power of 5 halves. Once we have found K, we can substitute K into the total cost formula to get this formula, which is a function of V and N. V is the velocity and N is the trip length in miles. To find the optimum value of the design variable V, we can calculate the first derivative of the total cost with respect to the velocity and set this to 0. I believe all of you know how to perform differentiations, and therefore I won't go through with you the step one by one. Okay, this is the general formula showing how the differentiations here is performed. If you have any issue to differentiate, please let me know in the forum for group 2 in Spectrum. In this differential equations, since N is a multiple for both terms on the left of this formula, it can be removed, leaving V as a single variable. Work all the way down, eventually you will get V equals to 490.68 miles per hour. How do you know that the velocity you have found in the solutions to question A minimizes the total cost? We can check the second derivative to confirm a minimum cost solution. Here we differentiate the previous formula one more time to get the second derivative. Because V is positive, we will get the second derivative with a value greater than 0. Therefore, the company concludes that V equals to 490.68 miles per hour minimizes the total cost of this particular airplane's flight. This is the second example. Energy savings through increased insulation. This example deals with a discrete optimization problem of determining the most economical amount of attic insulations for a large single-story home in Virginia. In general, the heat loss through the roof of a single-story home is given by this formula. The heat loss in BTU per hour is equal to the product of the changes of temperature in Fahrenheit degree, area in square foot, and the conductance in BTU per hour per square foot per Fahrenheit degree. The BTU here stands for British Thermal Unit. This formula can be written down in symbolic form as shown here. The changes in temperature is given by the difference in the inside and outside temperature. In Southwest Virginia, the number of heating days per year is approximately 230, and the annual heating degree days equals to 230 days multiplied with the difference in the average inside temperature and the average outside temperature each day. Consider a 2,400 square foot single-story house in Blacksburg. The typical annual space heating load for this size of a house is 100 million BTU. That is, with no insulations in the attic, we lost about 100 million BTU per year. Common sense detects that the no insulations alternative is not attractive and is to be avoided. The calculations of this 100 million BTU is given here based on the formula above. This 100 million BTU is equivalent to the product of the changes in temperature, area, and the conductance. And this 0.397 here is the U factor with no insulation. With insulations in the attic, the amount of heat lost each year will be reduced. The value of energy savings that results from adding insulations and reducing heat loss is dependent on what type of residential heating furnace is installed. For this example, we assume that an electrical resistance furnace is installed by the builder and its efficiency is near 100%. Now we are in a position to answer the following questions. What amount of insulations is most economical? An additional piece of data we need involves the cost of electricity, which is $0.074 per kilowatt hour. This can be converted to dollars per million BTU as follows. The 1 kilowatt hour is equal to 3,413 BTU, and this is equivalent to 293 kilowatt hour per million BTU. And this amount of energy can be converted into dollars by multiplying it with the cost of electricity per kilowatt hour, and we get $21.75 per million BTU. The cost of several insulations alternatives, the investment cost, and the associated space heating loads or annual heating loads are given in this table. An R value indicates the resistance to heat transfer. The higher the R value, the less the heat transfer, and the better is the insulation. In view of this data, which amount of attic insulations is most economical? The life of the insulations is estimated to be 25 years. To solve the questions, we can set up a table to examine the total life cycle cost. This involves calculating the total cost over the life of the insulations, which is 25 years. The total life cycle cost can be obtained by summing the investment cost and the cost of heat loss over 25 years. For example, the total life cycle cost of R11 is $40,837.50. This is obtained by summing the investment cost of $600 and the cost of heat loss over 25 years, which is $40,237.50. To calculate the cost of heat loss over 25 years, we can first calculate the cost of heat loss per year. This is obtained by the following formula. The cost of heat loss per year is equal to the product of annual heating load and the cost of electricity. The annual heating load for R11 is 74 times 10 to the power 6 BTU per year, and the cost of electricity is $21.75 per million BTU. Okay, these multiplications give us the cost of heat loss per year for R11 equals to $1,609.50 per year. Okay, the cost of heat loss over 25 years can then be calculated by multiplying this value with 25 years to get $40,237.50. Okay, similar calculations can be applied on other alternatives. Okay, comparing all the alternatives, we noted that the total life cycle cost for R38 is the lowest. Okay, therefore, to minimize total life cycle cost, we should select R38 insulations. Okay, these conclusions may change when we consider the time value of money, which means interest rate is greater than 0. In such a case, it will not necessarily be true that adding more and more insulations is the optimal course of actions. We will look at time value of money in the other lecture. Now we will move on to present economy studies. When alternatives for accomplishing a specific task are being compared over 1 year or less, and the influence of time on money can be ignored, engineering economic analysis are referred to as present economy studies. The rules or criteria used to select the preferred alternative depends on whether defect-free output or yield is variable or constant among the alternatives being considered. We can use these two rules to select the preferred alternative. We use Rule 1. When revenues and other economic benefits are present and vary among alternatives, we choose the alternative that maximizes overall profitability based on the number of defect-free units of a product or service produced. On the other hand, we use Rule 2 when revenues and other economic benefits are not present or are constant among all alternatives. In Rule 2, we consider only the cost and select the alternative that minimizes total cost per defect-free unit of a product or service output. Let's take a look at one example where Rule 1 is applied. Choosing the most economical machine for production. Two currently owned machines are being considered for the production of a part. The capital investment associated with the machines is about the same and can be ignored for purposes of this example. The important differences between the machines are the production capacities, which is given by the product of the production rate and the available production hours, and their rejection rates, which is the percentage of parts produced that cannot be sold. Consider the following table. There are two machines, machines A and machines B. The production rate of machines A is 100 parts per hour, and the production rate for machine B is 130 parts per hour. The hours available for productions is 7 hours per day for machine A and 6 hours per day for machine B. Percent parts rejected is 3% for machine A and 10% for machine B. The material cost is $6 per part, and all defect-free parts produced can be sold for $12 each. For your information, rejected parts have negligible scrap value. This is our assumption. For either machine, the operator cost is $15 per hour, and the variable overhead rate for traceable cost is $5 per hour. There are two questions here. Question A. Assume that the daily demand for this part is large enough that all defect-free parts can be sold. Which machine should be selected? Question B. What would the percent of parts rejected have to be for machine B to be as profitable as machine A? This is the solutions for questions A. Assume that the daily demand for this part is large enough that all defect-free parts can be sold. Which machine should be selected? Okay, Rule 1 applies in this situation because total daily revenues and the total daily cost will vary depending on the machine chosen. Therefore, we should select the machine that will maximize the profit per day. Okay, this is the formula to calculate the profit per day. Okay, so profit per day can be obtained by subtracting cost per day from the revenue per day. Okay, in detail, okay, this formula is divided into three parts. Okay, this part corresponds to the total daily revenue. Okay, this part corresponds to the total daily material cost, and this is for the total daily operator and traceable cost. The total daily revenue is obtained by multiplying the production rate with the production hour and the selling price as well as the percent parts accepted. Okay, the product of production rate and production hours here corresponds to the production capacity or the number of parts produced per day. Okay, for the total material cost, it is obtained by multiplying the production rate with the production hours and the material cost per part. Okay, here again corresponds to the production capacity. Okay, for operator and traceable cost, you can obtain the total daily operator and traceable cost by multiplying the summations of the total cost and traceable cost per hour with the production hours. Substituting the values of variables in the equations shows that machine A can generate a profit of $3,808 per day, whereas machine B generates slightly lower profit of $3,624 per day. Okay, therefore, we would select machine A to maximize profit per day. Okay, this is the solutions for question B. Question B asks, what would the percent of parts rejected have to be for machine B to be as profitable as machine A? Okay, to solve these questions, we need to find the break-even percent of parts rejected X. Okay, to accomplish this, we use the same formula for the calculations of profit per day for machine B, except that we replace the percent part rejected with variable X and set the formula equals to the profit per day of machine A, which is $3,808 per day. And then we solve for X. Okay, X can be found to be equals to 0.08. Okay, this means that the percent of parts rejected for machine B cannot be higher than 8% for it to be as profitable as machine A. In many cases, economic selections among materials cannot be based solely on the cost of materials. A change in material will affect the design and processing cost as well as the shipping cost. Okay, this example is about total cost in material selections and is the demonstrations of the applications of rule number 2. Choosing the most economic material for a part. A good example of these situations is illustrated by a part for which annual demand is 100,000 units. The part is produced on a high-speed turret lathe using 1112 screw machine steel costing 30 cents per pound. A study was conducted to determine whether it might be cheaper to use brass screw stock costing $1.40 per pound. Because the weight of steel required per piece was 0.0353 pounds and that of brass was 0.0384 pounds, the material cost per piece was $0.0106 for steel and $0.0538 for brass. However, when the manufacturing engineering department was consulted, it was found that although 57.1 defect-free parts per hour were being produced by using steel, the output would be 102.9 defect-free parts per hour if brass were used. Which material should be used for this part? Okay, for your information, the machine attendance is paid $15 per hour and the variable or the traceable overhead costs for the turret lathe are estimated to be $10 per hour. This is the solutions. The comparison of total cost per piece for the two types of materials, the 111 steel and brass, is shown here. The total cost per piece is estimated from the material cost, labor cost, and the variable overhead cost for each piece of part. Material cost per piece is calculated by multiplying the material cost per pound with the weight of material required per piece in pound. And this is giving us $0.0106 for steel and $0.0538 for brass. For labor cost per piece, we divide the labor cost per hour by the number of defect-free parts produced per hour. Similarly, for variable overhead cost per piece, we divide the traceable overhead cost per hour by the number of defect-free parts produced per hour. Okay, the summations of the material, labor, and variable overhead cost per piece will give us the total cost per piece. Okay, the total cost per piece by using steel is $0.4484 and by using brass is $0.2968. Okay, therefore, the saving per piece by use of brass is $0.1516. Okay, because 100,000 parts are made each year, revenues are constant across the alternatives. Rule 2 would select brass, and X use will produce a savings of $151.60 per thousand, and this is equivalent to a total of $15,160 for the year. And this is obtained by multiplying the saving per piece by use of brass with the number of parts produced each year. It is also clear that costs other than the cost of materials, such as the labor and overhead costs, were important in the study. In addition to deciding what material a product should be made of, there are often alternative methods or machines that can be used to produce the product, which in turn can impact the processing cost. Processing times may vary with the machine selected, as may the product yield, as we have seen this in previous example. Before we look at another example on choosing the alternatives, which are making versus purchasing, let me briefly go through the scenario. In the short run, 1 year or less, a company may consider producing an item in-house even though the item can be purchased or outsourced from a supplier at a price lower than the company's standard production cost. This could occur if direct, indirect, and the overhead costs are incurred regardless of whether the item is purchased from an outside supplier, and the incremental cost of producing an item in the short run is less than the supplier's price. At the short run cost of make versus purchase decisions are the incremental cost incurred and the opportunity cost of the resources involved. The incremental cost is the cost added by producing one additional unit of a product or service. Opportunity cost is the cost of the best rejected or foregone opportunity and is often hidden or implied. And because engineering economy often deals with changes to existing operations, standard cost may not be too useful in make versus purchase studies. Standard cost is the planned cost per unit of output. They are established in advance of actual productions or service delivery. Since standard cost is the projected cost, it may lead to uneconomical decisions. The following example illustrates the correct procedure to follow in performing make versus purchase studies based on incremental cost. To produce or not to produce, that is the questions. A manufacturing plant consists of three departments, A, B, and C. Department A occupies 100 square meters in one corner of the plant. Product X is one of several products being produced in Department A. The daily productions of Product X is 576 pieces. The cost accounting records shows the following average daily production cost for Product X. Direct labor costs involve one operator working 4 hours per day at $22.50 per hour, including fringe benefits plus a part-time foreman at $30 per day. This gives a total direct labor cost of $120. And this $120 is obtained by multiplying 4 hours per day with $22.50 per hour, plus the $30 per day for the foreman. The direct material cost is $86.40, and the overhead rate is 82 cents per square meters of floor area, and this yield the overhead cost of $82, considering Department A occupies 100 square meters. Adding these costs together, we get total cost per day of $288.40. The department foreman has recently learned about an outside company that sells Product X at 35 cents per piece. Accordingly, the foreman figured a cost per day of $201.60, and this is obtained by multiplying the selling price of Product X and the number of Product X produced per day. This results in a daily savings of $86.80. Comparing if the product is purchased from the company rather than produced in-house. Therefore, a proposal was submitted to the plant manager for shutting down the production line of Product X and buying it from the outside company. Do you think the foreman did the correct analysis? Let's read further. After examining each component separately, the plant manager decided not to accept the foreman's proposal based on the unit cost of Product X for 3 reasons. First, direct labor. Because the foreman was supervising the manufacture of other products in Department A, in addition to Product X, the only possible savings in labor would occur if the operator working 4 hours per day on Product X were not reassigned after this line is shut down. That is, a maximum savings of $90 per day would result. Second, materials. The maximum saving on direct material will be $86.40. However, this figure could be lower if some of the material for Product X is obtained from scrap of another product. And third, overhead. Because other products are made in Department A, no reductions in total floor space requirements will probably occur. Therefore, no reductions in overhead costs will result from discontinuing Product X. It has been estimated that there will be daily savings in the variable overhead cost traceable to Product X of about $3 due to a reduction in power cost and in insurance premiums. This is the solutions which shows a more correct analysis. If the manufacture of Product X is discontinued, the firm will save at most $90 in direct labor, $86.40 in direct materials, and $3 in variable overhead costs, which totals $179.40 per day. This estimate of actual cost saving per day is less than the potential savings indicated by the cost accounting records of $288.40 per day as shown by the foreman, and it would not exceed the $201.60 to be paid to the outside company if product X is purchased, which means the purchase cost is actually higher than the actual savings of $179.40 per day. For this reason, the plant manager used Rule 2 and rejected the proposal of the foreman and continued the manufacture of product X. In conclusion, this example shows how an erroneous decisions might be made by using unit cost of product X from the cost accounting records without detailed analysis. The fixed cost portions of product X unit cost, which is present even if the manufacture of product X is discontinued, was not properly accounted for in the original analysis by the foreman. Now we move on to the last topic of today's lecture, trade-offs in energy efficiency studies. Energy efficiency affects the annual expenses of operating an electrical device such as a pump or motor. Usually, a more energy efficient device requires a higher capital investment than does a less energy efficient device. But the extra capital investment usually produces annual savings in electrical power expenses relative to a second pump or motor that is less energy efficient. This important trade-off between capital investment and annual electric power consumptions will be considered. If an electric pump can deliver a given horsepower or kilowatt rating to an industrial application, the input energy requirement is determined by dividing the given output by the energy efficiency of the device. The input requirement in horsepower or kilowatt is then multiplied by the annual hours that the device operates, and the unit cost of electric power to compute the total expenses of electric power. You can see that the higher the efficiency of the pump, the lower the annual cost of operating the device is relative to another less efficient pump. This is an example showing the trade-offs between capital investment and the annual electric power consumption. Investing in electrical efficiency. Two pumps capable of delivering 100 horsepower to an agricultural applications are being evaluated in a present economy study. The selected pump will only be utilized for 1 year, and it will have no market value at the end of the year. Pertinent data are summarized as follows. The two pumps are ABC pump and the XYZ pump. The purchase price for ABC pump is $2,900, whereas for XYZ pump is $6,200. The maintenance cost for XYZ pump is higher at $510 as compared to $170 for ABC pump. The efficiency for ABC pump is slightly lower at 80% as compared to XYZ pump at 90%. If electric power costs 10 cents per kilowatt hour and the pump will be operated 4,000 hours per year, which pump should be chosen? Recall that 1 horsepower is equal to 0.746 kilowatt. Here shows the solutions. The expenses of electric power for the ABC pump is given by this formula. 0.8 here is the energy efficiency of the pump, and the efficiency is given as the ratio of the output power to the input power. Since the efficiency of the pump is 80% and the output power is 100 horsepower, the input power to the pump is therefore 125 horsepower. 0.746 here is the conversion factor to convert horsepower to kilowatt, and the 10 cent here is the electric power cost per kilowatt hour, and this 4,000 hours per year here is the length of operations of the pump. By using this formula, we get the expenses of electric power for ABC pump is equals to $37,300. For the XYZ pump, the expenses of electric power is $33,156 by using the same formula. Thus, the total cost of owning and operating the ABC pump is $40,370, and this is obtained by summing the electrical expenses, purchase price, and the maintenance cost for a year for that particular pump. While the total cost of owning and operating the XYZ pump for 1 year is $39,866. Consequently, the more energy efficient XYZ pump should be selected to minimize the cost. Notice the difference in energy expenses of $4,144 that result from 90% efficient pump relative to an 80% efficient pump. This cost reductions more than balances the extra $3,300 in capital investment and $340 in maintenance required for the XYZ pump. Here shows the summary of what you have learned in this lecture. Understanding the cost concept is important when performing economic analysis. It is important that the meaning and use of various cost terms and concepts be understood in order to communicate effectively with other engineering and management personnel. This increases the precision of the project and ease in making decisions whether the project should proceed or not. The cost concepts are those assets relevant to business operations and decisions. For example, fixed costs, variable costs, direct costs, indirect costs, recurring costs, non-recurring costs, revenues, and overhead costs are those costs that you need to understand. At break-even point D prime, total revenue is equals to total cost. Profit occurs when total revenue is more than the total cost. And we can use present economy studies in engineering decisions by considering various monetary consequences that occur in a short period of time. With this, I end this lecture. Thank you for listening.